Hello, students. In this video, we'll explore the fascinating concept of refraction of light, a key principle in understanding how light behaves as it passes through different materials. Refraction is a phenomenon that occurs when light travels from one medium to another with a different optical density, causing it to change direction. Refraction of light is based on the idea that light usually travels in a straight line when moving through a medium of uniform density. However, when it crosses into a different medium, like moving from air into water or from air into glass, its speed changes, leading to a bending of the light ray. This bending is what we call refraction. The behavior of light during refraction can be described using the angle of incidence and the angle of refraction. When a light ray hits the boundary between two different media, it does so at an angle. The angle of incidence is the angle between the incoming light ray and a line perpendicular to the surface, called the normal. The angle of refraction, on the other hand, is the angle between the refracted light ray and the normal. The reason refraction occurs is due to the change in the speed of light as it moves between media with different optical densities. Light travels more slowly in denser media, such as glass, and faster in less dense media, like air. This change in speed causes the light to bend toward the normal when it enters a denser medium, and away from the normal when it enters a rarer medium. To give you an example, consider a rectangular glass slab. When a light ray passes through this slab, it first enters from air, bends toward the normal as it enters the glass, a denser medium, and then bends away from the normal as it exits the glass back into the air. The interesting part is that while the light ray changes direction twice, the emerging ray remains parallel to the incident ray, although it is laterally displaced. This lateral displacement depends on several factors, including the angle of incidence, the thickness of the glass slab, and the refractive index of the material. It is the perpendicular distance between the original path of the light ray and its new path after it emerges from the glass. The phenomenon of refraction leads to several interesting effects. For instance, objects submerged in water, like a pencil or a stick, appear bent or displaced when viewed from above. This is because the light rays from the object bend as they exit the water, creating an optical illusion of displacement. Similarly, the apparent elevation of objects underwater, such as a coin at the bottom of a glass, occurs because the light rays bend upward as they move from the water to the air, making the object appear closer to the surface than it actually is. Refraction also affects our depth perception when looking into a pool of water. The water may appear shallower than it is due to the bending of light rays as they exit the water. Additionally, refraction is responsible for the twinkling of stars, as the light from stars bends while passing through different layers of the Earth's atmosphere, causing the stars to appear to shift and twinkle. One of the fundamental principles governing the refraction of light is Snell's law. According to this law, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media. This constant is known as the refractive index, which quantifies how much a light ray bends when entering a new medium. The refractive index can be used to determine how light will behave when moving between different materials. When light passes through spherical lenses, refraction causes it to converge or diverge, depending on the type of lens. A convex lens, which is thicker in the middle and thinner at the edges, converges parallel rays of light to a single point called the principal focus. This lens can form both real and virtual images, depending on the position of the object relative to the lens. For example, when an object is placed between the lens and its focal point, the lens forms a virtual, magnified image. This is the principle behind magnifying glasses. Conversely, a concave lens is thinner in the middle and thicker at the edges, causing parallel light rays to diverge as if they are originating from a focal point behind the lens. Concave lenses always form virtual, erect, and diminished images, which appear on the same side of the lens as the object. These lenses are commonly used to correct vision problems like myopia or nearsightedness. To determine the position and characteristics of images formed by lenses, we use certain rules, including the parallel ray rule and the focal point rule. These rules help us construct ray diagrams to predict where an image will form and whether it will be real or virtual, upright or inverted, and magnified or diminished. When dealing with spherical lenses, it's important to follow the new Cartesian sign convention. This system standardizes how we measure distances in ray diagrams for lenses, ensuring consistency in calculations and predictions. According to this convention, distances measured in the direction of the incident light are positive, while those measured in the opposite direction are negative. The focal length of a convex lens is positive, while that of a concave lens is negative. The lens formula is a crucial tool in optics, relating the object distance, image distance, and focal length of a lens. By applying this formula, we can calculate the position of an image formed by a lens and determine its size relative to the object. The magnification produced by a lens is another important concept, indicating how much larger or smaller an image is compared to the object. Lastly, the measures its ability to converge or diverge light. The power is inversely related to the focal length, with convex lenses having positive power and concave lenses negative power. The total power of a combination of lenses can be found by simply adding their individual powers. Now here's a question for you to test your knowledge. What is the measure of the bending of light as it passes from one medium to another? Please share your answer in the comments. The complete curriculum for Class 10 is available on our channel. Check out all the links provided in the description below. Please make sure to like, share, and comment for more such videos.